Hello, everyone, and welcome to today's webinar. My name is Chris Neva, Marketing Operations Coordinator at Thermal Analytics and host of today's webinar. Our presenters today are Weston Early and Logan Cannell. Weston is a thermal CFD engineer at Thermal Analytics, Inc., where he applies his background in simulation, heat transfer, computer vision, and algorithm design to support research and modeling efforts. With dual bachelor's degrees in mechanical engineering, engineering mechanics, and computer engineering from Michigan Technological University, Weston brings a multidisciplinary perspective to thermal analysis, image processing, and data-driven simulation. His skill set spans software development, statistical analysis, 3D modeling, and closed-loop control systems, making him well-suited to work involving synthetic data generation and AI-driven thermal modeling. Logan is a thermal CFD engineer at Thermal Analytics, Inc., where he supports research and development efforts focused on advancing the thermal modeling of lithium-ion batteries. His work includes expanding TAI's battery library, developing methods to simulate thermal runaway propagation, and investigating battery cooling strategies using rapid flow. Logan also contributes to energy usage estimation projects that integrate photovoltaics, HVAC systems, and human comfort modeling. He joined TAI in 2022 after earning his BS in mechanical engineering from Michigan Technological University and completed his MS in mechanical engineering in 2023. Throughout today's presentation, you may submit questions in the questions box, which we will review at the end. We are also recording this webinar and we'll send you the link as soon as it becomes available. And with that, Logan, if you're ready, you may begin.
Hello, everyone. Today we'll be presenting our work on enhancing UAV detection in the thermal infrared with synthetic data and deep learning. We'll be going over our thermal analysis tool and EOIR rendering tool MuSES. We'll cover the setup of a few UAV thermal models that will be used to create a long-wave infrared dataset for AI/ML training. We'll go into how we change the background of our target model renderings to improve the performance of an AI/ML prediction algorithm with our software CoTherm, as well as a new capability we've been working on to composite target renderings into a new background. Finally, we'll look at these results of an AI/ML algorithm fully trained on synthetic data and how it performs on measured long-wave imagery. First, I'll provide a quick overview as to what MuSES is. So MuSES is a thermal solver and EOI rendering tool, which takes inputs such as 3D CAD geometry description, part material thicknesses and thermal properties, as well as boundary conditions such as sun location, the sky and background for radiation exchange, and air temperature and speed for convective heat transfer to properly set up an analysis environment. Once these are combined, we get a physical temperature prediction of a target. Coupling this with the surface properties set on the geometry, we can create specular diffuse images from a sensor, as well as spectral or broadband images displaying the radiance or apparent temperature of the target. In addition to these images, which can be used to show or used to create data sets for AI/ML training, like we show in this presentation, we can also get contrast metrics such as delta TRSS and contrast radiance. Being able to gather all this information from one software is what helps to make MuSES such a powerful tool for those who care about the IR spectrum. And this may sound like a lot of manual inputs to manage, but having control over this wide array of parameters allows for representation of custom or complicated scenarios. We also have a lot of great features that take the burden off the user when learning the software or when modeling difficult parametric scenarios. MuSES is a complete thermal analysis tool that means capturing accurate radiation, conduction, and convection phenomena through simulation and modeling. Some of these features that improves the software's ease of use are listed here, like automatic calculation of view factors, the automatic calculation of vertical or lateral conduction, and our convection library, which handles aerodynamic heating with specified relative airspeed and a built-in solar model to handle the sun's position, as well as direct diffuse or reflected solar, which can be overwritten for specific cases. After the completion of a thermal solution, results like these will be shown where you can analyze or export the transient or steady state solution of things like radiative, convective, conductive, or solar heat fluxes, temperatures, and various other parameters. This thermal solution serves as a basis for our EOIR radiance predictions. The thermals then couple with the optical properties on the geometry and specific wavebands and solution times to paint a diffuse radiance prediction which lacks directional effects and atmospheric effects. This is typically sufficient for non-reflective targets and offers a good trade-off between speed and accuracy. If these additional effects are desired, though, your target is very reflective, or if you're generating a data set like we are in our case, then a BRDF rendering can be calculated to include the effects as well as capture the use of a specific sensor by specifying things like field of view, spectral response, range, and a few other parameters. This highlights the typical workflow to get a high fidelity rendering, starting from the thermal solution to the diffuse radiance prediction to the BRDF rendering. The combination of all these features allows us to successfully model numerous sophisticated targets and scenarios. A few examples that we've completed and is in our target model library can be seen here, specifically the modeling of UAVs, both big and small, battery powered and internal combustion driven engines. And although it is a challenge to model these assets, we've created a repeatable target modeling methodology to account for the key signature drivers of these systems. Here we're showing a larger UAV in the CH-4, a battery-powered Skylark model, and a more commercially sized quadcopter, which is also battery operated. A few additional targets can be seen here, incorporating aerodynamic heating, internal heating due to motors, or the IC engines. In this presentation, we'll discuss an image data set created using the following UAV models, ran over a 6-hour period, where the top row shows battery-powered UAVs and the bottom shows a few of those powered by IC engines. Additionally, we'll include confusers by modeling 3 different birds using a simple thermoregulatory system with an assigned core temperature to increase the variation of these bird models in the dataset. 3 different wing positions will be modeled. All of the dataset renderings were automated with our tool CoTherm. The process for this dataset creation altered between the 6 UAV models with 2 different rotor positions for the rotored UAVs and the 3 birds with 3 wing positions each. Additionally, the backgrounds were varied between 3 different scenes, a hot, cold, and mild environment. The renderings were taken from various times in the solution with multiple sensor positions, ranges, and aim point variations. In total, this created 38,000 renderings for the dataset. To test the dataset, we used an automatic target detection algorithm called YOLO 11 from Ultralytics. This is a Python-based algorithm that is pre-trained on the COCO dataset. Important to note is that for our training, we only use synthetic imagery, and we broke our data set into 3 separate pieces. 80% of the data was used for training, 10% was used for validation, and the remaining 10% were saved for follow-up testing of the algorithm. To evaluate the performance during the validation of the algorithm, we chose the metric mean average precision, which includes overlapping thresholds that consider true positives, true negatives, false positives, and false negatives. As you've seen, a lot of different information goes into making a target model, and adjusting all of it manually to create an image data set can be tedious. However, we can automate some of that with another TI developed software, CoTherm. So I'll hand it over to my co-speaker, Weston, who will cover that more, as well as go into the backgrounds used in this data set, specifically stitching the targets into a less uniform background for improved realism and algorithm performance.
All right, we'll begin to go over the image data set generation with CoTherm. So our approach for generating the image library includes starting with generating the data sets for training algorithms utilizes the multi-stage process shown here. This process maximizes accuracy and efficiency. Inside of each model, we have geometry of the target from our existing database, optical surface descriptions, and terrain descriptions. These models are fed into MuSES with weather data and sensor parameters to output renderings in the desired spectrum. And the rendered images are then used to train any recognition algorithm to identify and classify the different models. To generate these types of data sets, CoTherm is our tool of choice. CoTherm is a co-simulation and process automation tool. It's often used for complex multi-physics simulations that require coupling multiple software packages together, but it can also be used to automate repetitive process like MuSES thermal and infrared predictions over a wide range of variables. The CoTherm user interface is shown here. There is a process flowchart made up of series of simple tasks that run to completion. So we're able to provide a GUI-based path for generating these large IR data sets of interest in an efficient manner. As of CoTherm 2025.1, a standard process, parallel BRDF rendering, is available for generating a large set of BRDF renderings efficiently using parallel processing. This process is included in the example folder of every CoTherm install. The process automates the calculation of both the thermal diffuse radiosity solutions, if not already completed, and the BRDF renderings. The user inputs can be quickly set up to define one or more models to be rendered and the parameters that dictate what set of renderings will be generated. Along with the models, the template BRDF configuration file is given, which will be modified with the parameters to be varied for each rendering. All other parameters of that template BRDF configuration file will be maintained. During or after the running process, a set of DAT files and PNG files will be created for each rendering for each model. The images on this slide show a few of the images created by the standard provided example. The included example simply creates these files and exits, but CoTherm's process flexibility makes it easy to extend the process to organize or analyze the rendering results in custom ways, including applying post-processing steps to the produced images and passing the rendered images on to AI/ML training processes used for target recognition or other applications. These extensions are usually straightforward using built-in CoTherm features, and TAI's technical support can be engaged to help with process extension. Training AI/ML algorithms to identify vehicles based on their thermal signature is a complicated task. It is just as important to identify what is the subject in a scene as it is to identify what isn't the subject. Training an algorithm with a dataset of uniform background renderings, such as the ones that MuSES provides, does not typically provide the context necessary to distinguish the subject from the background. One feature that distinguishes CoTherm from simple batch file scripting is its ability to include custom post-processing steps in the rendering process to include different types of backgrounds and distractors in the training dataset. This increases the robustness of the trained algorithm, leading to it yielding stronger detection results. One such post-processing step is fractal cloud generation. Fractal clouds refer to artificial clouds generated with Perlin noise, a computationally inexpensive method to produce realistic-looking cloud effects. Models trained on data processed with fractal clouds yielded stronger recognition of models in aerial environments with clouds present. Another post-processing step that can be applied to the rendering process to increase recognition performance is image compositing. Thermal Analytics has developed a custom image compositing process that can extract a simulated model from a rendering and stitch it into a measured background image. We have developed a process that can produce the renderings needed for the dataset, composite them into a background image, and apply the necessary post-processing steps to produce realistic images of simulated drones in measured background images. This process works by first producing a BRDF rendering of the drone model, extracting the pixels of the rendering that belong to the drone's elements, and inserting them into a measured image of the sky scene with blurring and other post-processing steps applied to maximize the accuracy of the simulated scene. Another post-processing step that we apply to composite images that sets our data set apart from others is our ability to create artificial rotor blur. MuSES is limited to producing renderings of only stationary objects, and it is not able to account for the effects that shutter speed has on an image. In reality, the propeller blades of a drone are moving at a fast enough rate that a typical camera shutter would be open for a fraction of, if not an entire rotational period of the blades. This produces what is known as rotor blur and can be seen in the images in the bottom left. The image taken in the long wave IR spectrum on the left has a slower shutter speed or integration time than the image taken in the mid-wave IR spectrum on the right. This difference in integration time changes the amount of rotation the blades sweep through during the period of time the sensor's shutter is open, and therefore produces the two distinct rotor blur shapes seen in the two images. The calculated shapes used to replace the pixels in the image with the artificial rotor blur are shown in the bottom right in red, representing the two different integration times common in the field test images. Once the shape of the blur pattern is calculated based on the geometry of the drone and its orientation in the rendered image, the pixels are inserted into the composite image. While inserting, the process removes any pixels associated with the stationary blades and replaces them with the blur pattern, while also determining which parts of the drone are between the blade path and the sensor to ensure they are not incorporated in the inserted rotor blur effect. The final outcome of this process is shown in the image in the top right. The drone on the left in this image is a DJI Mavic 2, whose thermal signature was measured with a FLIR E60 long wave IR thermal camera. The drone on the right in this image is a simulated DJI Mavic 3 that has been composited into this measured image with the rotor blur effect applied. The image compositor can also be used to expedite the process of generating vehicle imagery against a ground plane. Computing view factors between an aerial vehicle and every element on the ground plane is a very computationally expensive task. Each target translation also requires the recomputation of view factors and thermal results, slowing down the overall dataset generation process. By combining a synthetic target with a pre-generated synthetic background, it allows for more target placement flexibility and more efficient dataset generation. Next, I will go over a brief demo of how the image compositor is set up and utilized for dataset generation. Here's the image compositor CoTherm process. This process takes a list of models, a list of rendering parameters, a set of measured backgrounds, and user-defined parameters, and produces datasets of the rendering stitched into measured background images. The Key Properties tab here is where each of the input file parameters are defined to control the current run. The message window here displays information about the current run. To set this up, select a measured background image CSV file to composite each model into. If multiple background images are available, the user can enable the random background selection key property here, and the process will select random background from the directory for each rendering. To enable or disable the scaling of the measured background to match the average temperature of the simulated background in the thermal model, select this key property match average temp. This increases the accuracy of the composite image by placing the model in a similar environment to that which it was simulated in. Next, select the model and render table CSV files. These files contain the file path of each model and the rendering configuration parameters for each rendering, respectively. Here's a sample rendering table CSV file containing the parameters for each rendering, and a sample model table CSV file containing the file paths. If the view factors and thermal solutions are not present for any of the models in the model table, these key properties here need to be enabled in order to compute those. If there are propeller blades present on the model and the rotor blur effect is desired, enable the rotor blur key property and configure the rotor blur parameters in the composite config table key property. Each of these parameters controls the visual appearance of the rotor blur, such as the relative temperature of the inserted pixels, the radius of the blur effect, the method and level of the blur applied, and the shape of the blur arc. Different blur arc lengths simulate images captured with different integration times. And to randomize the arc length of every image generated, enable this key property here. Finally, select which output types are desired for each rendering. Once everything is set up, this process is started by clicking the run button at the top. The process can also be configured to utilize multiple cores at a time using this parameter here. It will first initialize the tables and scripts needed for the process, and it skips the thermal and radiosity calculations as those are already available for this model. It then performs the BRDF rendering using a MuSES license. The target is extracted from the rendering and inserted into the selected background image. Post-processing is then applied based on the user's selection and specified file format, and the specified file formats are produced. Here are a couple sample composite images produced by this process. And for single image generation, it can be helpful to specify the location of the target being inserted into the image. To demonstrate this, I'll restart the run with the target insertion key property enabled. This will trigger the code to prompt the user with this user interface, allowing them to select the target placement in the image. After the compositing process is complete, here is the produced image. Here are another couple sample images with the distractor birds and a few of the other models. These images include fixed wing assets, copter style assets, and the bird confusers, all composited into measured backgrounds. This data set was used for training and testing and yielded the following final results that Logan will be describing.
All right, so here are some of the training results of our synthetic data set. Specifically, we have a confusion matrix showing the percentage of images that were labeled a specific object. The horizontal axis shows what the image was depicting, while the vertical axis shows what the algorithm labeled the image to be. This means that the higher number along the diagonal, the better the algorithm is at labeling the images correctly. This confusion matrix only shows the results from the images that were in the validation, so they were not ever seen by the algorithm before this labeling. Additionally, we show results of the bounding box that the algorithm puts around what it thinks an object is, if it detects it, what it labels the object as, and how confident it is that the object is that assigned label. We can see here that the tested images were 2 synthetic images with a fractal background that contains a confuser bird as well as a target UAV. The algorithm is able to detect the UAVs in both images with very good confidence, as well as correctly detect the confusers. You can also see that the algorithm correctly boxes out the target without missing pieces of it or getting too much of the background. Even more impressive is that when we use this algorithm that was fully trained on synthetic data to test measured IR imagery of a Mavic 3 drone, you can see here that it was able to accurately label the Mavic with great confidence. Again, you can see that the bounding box didn't miss any of the target, even though there is blur due to the rotor's movement. We also wanted to test the algorithm with images that contained backgrounds it had never observed before. We tested the algorithm with synthetic imagery on a uniform background and a composited fractal background that included rotor blur. When just comparing the drones, you can see that the mean average precision is always higher when using a fractal background with rotor blur than the base uniform background rendering alone. The largest gaps appear in the Mavic 3, where the blur has a large impact due to the rotor's size compared to the drone body itself. And this impacts the algorithm's ability to detect it correctly. A subset of the algorithm's predictions can be seen here, highlighting the effect that the alternate background has on the image's realism and the algorithm's ability to detect it. Here is how we're leveraging the AML datasets for detection and recognition purposes. Continuing to use the previously mentioned YOLO algorithm, which was fully trained on synthetic and target models using rotor blur and composited onto a measured background with 6 unique UAVs and 3 bird confusers. We deconstructed a field test video of a Mavic 3 frame by frame and fed it each of the frames into the algorithm. We then reconstructed each resultant frame back into the final video that you will see here in a moment. The Mavic 3 will start out in one orientation against a tree cluttered background. It will then rotate 90 degrees and rotate back. Then it'll raise an elevation to a partly cloudy sky background. This video shows that the algorithm accurately highlights the Mavic 3 apart from a few frames where it picks up on the tree background. This is not surprising as the algorithm was only trained using cloudy backgrounds. You'll see that besides these few frames, it also labels the object as a UAV and more specifically, a copter style UAV, where it fluctuates between the Mavic 3, the NX-110, and the Thesis. As it rises above the trees, you'll see that the confidence in the label increases and it no longer misidentifies the object as a different copter UAV. We additionally did some testing using our algorithm trained with a combination of synthetic UAVs and birds on a measured long wave video of seagulls to see how it compared to an algorithm fully trained on our synthetic bird models. You can see that the combined algorithm does an okay job throughout the video at identifying the objects of interest, with a few exceptions where it picks out groups of snowflakes as the drone. You'll notice that it misidentifies the target frequently as a drone of some kind. It sometimes even labels the two birds together as one drone. The algorithm trained only on synthetic birds does a much better job and never mislabels snow as a target. It does, however, occasionally miss one of the birds. So in conclusion, we demonstrated a workflow for creating a large data set of synthetic long-wave IR imagery, as well as demonstrating the capabilities of adding after image effects like rotor blur or image compositing. We found that these effects are especially important for improving the performance of moving targets with rotors like UAVs. Finally, we showed that you can train a detection algorithm using only synthetic imagery as a supplement or alternative to training on measured imagery. Also, just would like to point out that we have a few additional upcoming webinars on October 9th and November 6th. And with that, we can answer any questions. Thank you.
All right. Thank you, Weston. Thank you, Logan. You go ahead and open up for some questions here. What countermeasures are in place in the compositing process to reduce the effects of stitching artifacts on the trained algorithm?
Yeah, so stitching effects are a pretty common problem when using synthetic composite images for training AI ML algorithms. And that refers to kind of the border between the inserted target and the measured background. So we have a couple of different blurring effects that we apply to this region, one of which is called a Gaussian blur that applies a pretty standard Gaussian blur filter to the target, as well as a couple border pixels between the target and the background. And another we apply is known as super sampling, where you basically scale up that region and then scale it back down to its original size. And every cycle of this blurs those pixels together. And we found that a combination of the two is most effective to combat those effects.
Thank you. What is the estimated time savings of this composite process versus doing manually?
The manual process kind of depends on which software you're using, but I'd say we estimate that each image would take anywhere between 5 and 10 minutes to produce, whereas this CoTherm process is producing 10, 15, 20 images in that same period of time. So it's a pretty big factor of increase in efficiency.
Okay, thank you. In slide 41, why is the drone better detected in the fourth image than in the third when one has blur background and the other has no background?
Yeah, so I think the main reason is the algorithm that we tested was tested on a composited data set that included rotor blur. So you can see that when the image on the left doesn't include that rotor blur, the algorithm hasn't really seen an object like that before. So it just does what it thinks the closest thing would be, in this case, the seagull. But I think it's important to note that adding the rotor blur effect really does improve the realism and the abilities, or the algorithm's ability to detect measured imagery.
All right. Well, it looks like that will do it for questions. So that will complete today's webinar. We appreciate you all for attending. You will receive a follow-up email later today containing a link to watch the recording of today's webinar session. Again, thank you all and have a nice day.
Thank you.